Hi, this is Decision and Control Team. We're going to give you a presentation. First, let's talk about the decision part. Last semester, we implemented real-time rule generation for obstacle avoidance. However, in the case of path generation, the optimal path could not be generated due to various environmental changes and sensor noise. So the path is not created. It has been implemented to avoid obstacles by searching for a target point in real time. The following is a demo video of avoidance driving performed with the algorithm implemented this semester. You can see how it avoids obstacles with minimal steering. Obstacle information is transmitted from LiDAR to segment line, extended line by a certain distance d, and selected points as a target point. If two or more obstacles are detected, the nearest obstacle is prioritized to avoid it. How to get the target point at this time is, first, we can have the end point of segment line and the slope, and find the target point using the trigonometric formula. This is very simple. Furthermore, it can dodge obstacles effectively. Implementing in this way, we ran into one problem. Since the current area of interest of LiDAR is 180 degrees, the target point is directed towards the obstacles like this. Because the vehicle is trying to steer sharply towards an obstacle, it is more likely to crash. To solve this, we use the following method. If the segment line does not cross the reference line, the current driving direction is maintained as it is. Besides, the measured value of LiDAR is unstable due to environmental factors. There are limitations that are not integrated with the lane keeping algorithm. Next semester, we plan to conduct research in the direction of overcoming these limitations. The following is the new implementation in this semester. Lane keeping driving and narrow road driving both work in the same way. This is a demonstration video of driving on a narrow road. Currently, the lane keeping driving test has not been completed, so I'll tell you in advance that I can't show it. Target search is performed when lane or narrow lane information is given. It is divided into two cases. Of this, I'll tell you about the second case. When only one lane or obstacle is detected, the vehicle drives while maintaining a certain distance from that line. It is calculated using a trigonometric formula similar to the previous avoidance driving. In this case, different formulas are applied to the left and right lanes. We also study U-turn and parking in this semester. We needed sensor data of the vision team in the U-turn and the data of LiDAR team in the parking. We received lane recognition data and sign data from the vision team and the number of available parking spaces from the LiDAR team. In the case of U-turn, the vehicle recognized the U-turn sign, and then it keeps driving. We will look at parking with the image data. After recognizing the parking sign, the vehicle changes to parking mode. By reducing the speed of the vehicle, we can reduce bouncing of the LiDAR, and try to park according to the number of parking spaces received from the LiDAR. After a successful orthogonal parking, stop for 3 seconds. Then change to reverse gear and go back to original position. After that, driving along the GPP route. The following is an image on the simulator. At the lower right corner, the coordinates of the obstacles are received. The red is the parking space, and the white dot is the information of the obstacles, although it is hard to see. This is an overview demo video of parking. This is an area that needs to be improved in the next semester. The vision team will improve it so that when a sign is recognized, it can be changed to each mission mode. So now we're gonna start to talk about how we deal with control vehicle. There are two parts mainly, longitudinal control, which is about speed, and lateral control, which is about steer. The two controls interact each other to decide what the next behavior of vehicle would be. Let's start with longitudinal control first. Through this semester, we found that our vehicle reached to the target speed too slowly. So no matter which target speed ERP take, we try to make it get to that speed as fast as possible, then maintain the speed with stability. For that, we set up a p-gain value up. As a result, we got this graph. The problem was though, after it hit the target speed, it loses its output for seconds. We thought that was because there might be some problems in hardware or small sync on the track might affect. As you can see a graph on the right side, the target speed is different at every curvature. Speed of vehicle got some delay compared to the target speed. We assume large of safety factor of target speed makes fluctuation to the target speed, so that ERP couldn't catch up the speed. We also got understeer problem, so we readjusted the look-ahead value, but the vehicle got far away from the lane. We tried to reduce the errors as much as we can. Thus, we proceed with PID gain tuning on a longer straight path to solve the problem of velocity drop. And lateral control has begun the study of MPC control, a new control technique, to solve the understeer. We also received information of 70-meter track on the ground which is more flat than the other, so that we could minimize possibilities occurred from the errors. Then, we went through lots of trials with the values we gave intuitively. We thought we could make up for the limitation of P gain as we trade I and D gains. We added D gain, which acts as a damper, judging that the drop is large as it goes up quickly due to P control. However, there was steady error value that could not be closer, so we added I gain including cumulative error value. But as you can see here, as long as it gets to target speed, there was repeated rapid reduction on the speed. We finally got to the conclusion that the drop of speed wasn't because there might be small sync or some problems on hardware like we assumed before, but there was discrepancy between V-in the system took and V-in the controller should for it. We wanted to see how it goes visually, so we put V-in value on the graph. You can see the yellow line on the graph, that's V-in the system take from the controller. It shows that the moment when the vehicle hit the target speed, it returned zero value right away. And this tells us we could never fix this up by adjusting PID gains pretty sure. Different from as general, we gave the manual speed to the vehicle directly, not to adjust power of the motor. So no matter how large P value we put in, once overshoot occurred, we couldn't help putting 0 or minus value for input. This looks very simple, but we haven't done this before, so we couldn't realize right away. By doing this, we learned one lesson. When it comes to the control, figuring out how the system would behavior is always the first order. We recognize the limit of senior controller and specify the minimum speed limits. We were able to get pretty sure good outcome. But still, we got a similar problem at curvature with the same PID gains. We set up the lower boundary of speed. So in the red section right here, you can see V-in follows V-reference. The fact is, it is supposed to be like the one in the green section, because the red section is where the vehicle is getting out of the curve. If we didn't set up the lower boundary of speed, V-in would have been way much lower than the V-reference in the red section. We need another improvement on PID gains to make the vehicle get to the target speed at the curve. To apply the PID controller, we use the Ziegler-Nichols method during the PID tuning process. The Ziegler-Nichols method is divided into two types, the first of which is to determine the PID gains using the system's response to step input. First, draw a tangent line to the inflection point of the response curve as shown above. Then, determine the time constant t, L, based on the points where this tangent meets O and gain k. Finally, use the table above to determine the PID gains. This is the first method. The second method uses transfer function of the plant. First, find the critical gain value where the responsive system reaches the marginally stable state when only proportional control is applied. Next, find P, the oscillating response curve, and determine the PID gain based on the organized table. This is second method. We choose the first method because of the characteristic of the vehicle system and the elements used in PID tuning. Since the vehicle system already includes the basic controller, so it is always a stable system. However, the second method as shown in the figure above can be used to tuning system that can be determine stability or instability according to the gain K. So critical gain K can be obtained, and information we can use is only time response to step input. Because we didn't know the exact transfer function of the vehicle system, we used the first Jiggler-Nichols method, which allows PID tuning with given information. We got these gains as a result of applying the first method to the response before we applied PID controller to ERP. We set these gains as PID gains, then ran some field tests. The reaction got better, but felt bad a little bit about the result. Even if the initial value of PID gains was found by above method, it was necessary to readjust the gain through repeated field tests to set the optimal gains according to the purpose and condition. As a result, the P gain was increased to increase the reaction speed to the target value, and D gain was properly increased to secure stability. Through this progress, we finally obtained these values. If the P gain is 50 or higher, there is no significant impact due to the upper limit of 20, so we have adjusted it to an appropriate value of about 50. Next, we will show you about the research of lateral control. We studied MPC control as an alternative to per pursuit. MPC is a method that uses control input optimized and obtained by minimizing errors about references of numerous points of future. This method has more powerful characteristics than PID controller. Also, can make a vehicle drive smoothly without sensitive reaction because it considers what the points of future would be. This is a dynamic vehicle model which is simplified using bicycle model. When it comes to real situation, driving direction and direction of tires are a little bit different because of deformation and slip. This is called slip angle, and alpha and beta correspond to it. We can make a model using Pazeka tire model and momentum equations. Say difference between tire's angle of rotation and the slip angle is small. Then you can linearize tangent theta to theta. We put some values into force and momentum equations. Then we got acceleration of y direction and the angle of rotation based on the vehicle. This is state space vector about the parameters. And we can make state space vector into these equations approximately. And in order to denote this model into code, transform location vector to discrete term. We found open loop system based on the dynamic modeling, and by repeating as much as change in the steering angle, which is given, generate a new state value. Therefore, we need to get steering angle after state value are optimized, and this will be obtained using cost function. The cost function is consisted of the references and errors based on psi and absolute y coordinate in state vector. Consequently, the smaller the cost function will be, the steering angle, psi, and absolute y coordinate will get the same value as reference does. The reason why we put steering angle delta is to minimize the change in steering angle so that the vehicle could show stable driving performances. Also, to find minimum value using characteristic of convex, you have to convert cost function into quadratic function. Next, I'm going to tell you how to convert vectors into matrix form of quadratic function. You want to get bias away, which doesn't have any effect on the result, because you have to find the vex value when quadratic function to get the minimum value. A gradient value of cost function will be minimum when it is 0. If you add the change in steering angle to the current steering angle at a point, you can find the optimal steering angle for the next loop. Then it is possible that lateral control will catch up the reference position in the optimal way with iterations. You can see how smoothly it catches up the reference position right here. But the problem is, this method isn't appropriate for the curve like U-turn, because this is basically designed for the straight lane. However, this problem will be solved easily by transforming the current position of the vehicle into relative coordinates, and we're working on it. The other problem is, it is hard to get perimeter properties. For this problem, you can just look up the data to find the tire friction coefficient and use software like UZ or NX to find the inertia of movement. Next, we will tell you about the progresses that new members went through in Control Team. Since all the new members are from mechanical engineering, we had to study basic programming. Also, we studied per-pursuit control theory, and we had to study rows, which is used in this project basically. For that, we studied the basic structure of node, package, topic, subscriber, publisher of rows, and practice Hello World, total shim by taking the lecture individually. Furthermore, we studied basic ROS commands and how to create the packages, and we used the ROSPy module to create the talker and listeners as Python files in the packages, send and receive messages in the form we wanted, and receive them in the terminal window. When it comes to Python, we study basic Python grammar and several modules by referring to the textbook and the lecture. In addition, we've tried the per-pursuit and recurve algorithm based on the bicycle model and wrote the code that follows the straight section. On the first run, index value kept on the starting point, so the vehicle moved away from the target lane. To solve this problem, we found the shortest path to target pace and set that point as the next index, so that we could get the point which is close to the target. Lastly is the research plan for the summer semester. First of all, we are planning to conduct a field test of local path planning and NPC control in July. After, in August, we will collaborate with the Vision and LiDAR team to carry out detailed missions, and we will conduct mapping and overall field tests to prepare for the competition. Thank you for listening, and special thanks to Professor Hal Kim and Professor Guan.